Okay, so let's talk about drawing free body diagrams. So free body diagrams are something that we draw when we do Newton's second law problems. So we need to learn how to do these before we start doing the more complicated problems. Now, all they are is they just show the forces that are acting on an object. So you can see this rock climber right here. The rock climber has the pull of the rope, which we call the force of tension. We also have the pull of gravity, which we call the force of gravity. And then he puts his little foot on the cliff. There's the normal force of the cliff to the left, and then the friction of the cliff to the right. So those are all the forces that are acting on his body. Now, I do want you to draw a free body diagram for every single problem you do. Yes, I mean every single problem that involves forces, you will be drawing a free body diagram. So there's some steps here. I have 5 steps to drawing a free body diagram. The first is to identify the object you're drawing the diagram for. If there are multiple objects, you will draw multiple diagrams. So you only want to draw these forces on one object at a time. Number 2, we want to identify the forces acting directly on the object. Number 3, we draw a box or a large dot for our object that we're drawing a free body diagram for. I'm partial to a box, but if you like a large dot, that's totally fine as well. Number 4, we're going to draw a vector to represent each force. We draw it from the object and in the direction the force is being exerted. So you'll see that these arrows come out of the object. Now you're also going to label the vector with the proper label, and it is important that you draw the magnitude of the vector, so the length of the vector, to kind of match the magnitude of the force. So if you have a bigger force in one direction, that arrow will be bigger than one of the other arrows that it's bigger than. And then last but not least, if there are any forces acting at an angle, you want to break them down into their X and Y components. We'll talk about that more in another video in this module. So when we show motion in free body diagrams, we know from Newton's first law, objects at rest stay at rest, objects in motion stay in motion at constant velocity unless acted upon by an unbalanced force. So what that's telling us is that when forces are balanced, which looks like this in free body diagrams. So notice how these arrows are balanced. They have the same length, so they have the same magnitude. The same with this one. This normal force balances out this force of gravity. The applied force balances out the force of friction. So that's how balanced forces look in free body diagrams. And when the forces are balanced, we either are at rest or we are in motion at constant velocity. So the key here is that when we have balanced forces, there are no accelerations, because remember, unbalanced forces cause accelerations. I'm blocking it right here. So unbalanced forces are what cause accelerations. And unbalanced forces in free body diagrams look something like this. Look at our applied force is larger than our friction force here. So this object is going to be accelerating to the right. And then here, our force of gravity is the only force acting on the object. So the object is accelerating downward because there's no force to counteract that force of gravity. All right, so let's do a couple examples. Well, a lot of examples. I think I have 9 examples total. So number 1, we want to draw a free body diagram of a physics book sitting on a desk. Now, remember, our first step to this is to identify the object. It's just a physics book. We know that it's sitting on the desk, but the object that is in question here that we're drawing a free body diagram of is the physics book. So we're not going to even really care about the desk. The desk is going to be causing a force on the physics book. But other than that, we're not drawing a free body diagram of the desk, okay? We're drawing a free body diagram of the physics book. So there's my physics book. I know, it's very beautiful. It's my little box of my physics book. Now, the first question I will ask you every single time you do free body diagrams, and what I want you to ask yourself is this object on the Earth? Yes, it is. So every time an object is on the Earth, we have the force of gravity, right? The force of gravity is what is causing this object to stay on the Earth. Now, the way that this free body diagram looks right now, it looks like it is accelerating downward, but we know that that object is at rest. So we have another force that is counteracting this force of gravity and that motion that it would cause if it wasn't present. We know that the physics book is sitting on the desk, it's going to be the force of the desk on the physics book holding it up. So that direction is upwards, and we call this force the normal force. The normal force is basically just a resting force. So for example, if this is the table and this is the physics book, it's upwards, and it's what is causing that physics book to be held up. It's supporting the physics book. The physics book is resting on the table. So that's why I like to call it a resting force or a supporting force. The reason it's called a normal force is just because a 90-degree angle, which is what this normal force makes with the table, that 90-degree angle back in the day used to be called a normal angle. So that's why they call it the normal force. And it's just stuck from now on. All right, so that's our first example. We can see that these forces are balanced, which makes sense. The object is at rest. There is no acceleration. All right, example number 2, we want to draw a free body diagram of a hockey puck being hit with a hockey stick on frictionless ice. So let's draw our hockey puck first. Look at that beautiful hockey puck. It's amazing. I know. Now, we know that this hockey puck is on the earth, so we have the force of gravity downward holding it on the earth. We also know that it is sitting on the ice, right? It's moving, yes, but it is resting on the ice. It's being supported by the ice. It's not accelerating downward. So we know that it also has a normal force supporting that hockey puck, holding it up on the ice like that. And then we know that it is being hit with a hockey stick. So I'm going to say that it's being hit to the right with that hockey stick, and we call that the applied force. So we have F sub A here. Now it says that this ice is frictionless, so I'm not going to draw friction. So this is our finished free body diagram. So as a result of this free body diagram, which direction are we going to accelerate? If you said to the right, you're correct, right? We have an unbalanced force to the right, that force applied, and therefore that is going to cause an acceleration to the right of this screen, right? Because remember, unbalanced forces cause accelerations, and those accelerations are in the same direction as the unbalanced force. So that's our example number 2. Example number 3, we have draw a free body diagram of a hockey puck sliding across the ice at constant velocity after it was hit. So again, here's my hockey puck. I know, it's very beautiful. I'm a very good artist. We are on the earth still, so this hockey puck is being held on the surface of the earth with the force of gravity acting downward on that object. It is still on the ice, and it's being supported by the ice. It's not falling towards the center of the earth, so we have the normal force upward. Now we know also that this hockey puck is sliding across the ice, and we know that it is after it is hit, so there's no more applied force here. We also know that it's sliding across the ice at constant velocity. So remember, constant velocity means there's no acceleration, which means that forces have to be balanced here. So this is our free body diagram. I know, it looks weird. It looks exactly like the free body diagram of the physics book sitting on the table at rest. But remember, when we don't have friction to slow this ice down, Newton's first law says that object in motion will stay in motion at constant velocity for infinity if there's no friction present, if there's no unbalanced forces to cause that object to change its motion. So this is kind of an example of Newton's first law. We have this hockey puck, which will theoretically slide across the ice at constant velocity if there's no outside forces slowing it down, which of course we know there is in real life, but we're just assuming that that ice is frictionless. All right, so that's example number 3. Example number 4, we want to draw a free body diagram of a soccer ball rolling across the grass after it is kicked with friction present. What happens to the soccer ball? So again, we're drawing a soccer ball. There's my soccer ball. Isn't it beautiful? Yes, I know. We know that we are on the earth, so the force of gravity is holding it on the surface of the earth. Again, that soccer ball is being supported by that grass. It's not falling into the center of the earth, so therefore we know that there has to be a normal force acting upwards on the soccer ball. Now this is after the ball is kicked, so there is no more applied force, and it's rolling across the grass. I'm going to say it's rolling to the right across the grass, and I know that friction is present. So we're going to draw a force of friction in here. If the ball is rolling to the right, friction is always going to oppose the motion of the object. So friction will be to the left. And this is our finished free body diagram. Now, my question for you is, what happens to the soccer ball? Well, if it's moving to the right, but the unbalanced force is to the left, and therefore the acceleration is to the left, that soccer ball will slow down and stop. Remember, if we called this a positive velocity, it's moving to the right, and then the acceleration is in the opposite direction. It's a negative acceleration. When velocity and acceleration are opposite signs, that object slows down. So that's what's happening here. Example number 5, we want to draw a free body diagram of a lawnmower being pushed across the grass at constant velocity. So again, here's my lawnmower. It is on the earth, so I'm going to draw the force for the force of gravity because it is keeping that lawnmower on the earth and not floating up into the sky. I also know that it's being pushed across the grass. So it is resting on that grass. The grass is supporting it, holding that lawnmower up on the surface of the earth. So we have a normal force upwards on that lawnmower. And then also I know that this lawnmower is being pushed across the grass. So I know that there is an applied force. I'm going to draw that applied force to the left. Now, as this free body diagram is, it looks like this lawnmower is accelerating to the right because I know that unbalanced forces cause accelerations. So since the problem tells me that this lawnmower is being pushed across the grass at constant velocity, there has to be a friction force present that is the same magnitude as that applied force because our forces have to be balanced if we're going at constant velocity. Because remember, constant velocity means no acceleration. Therefore, our forces are balanced. So this is our finished free body diagram for example number 5. Example number 6, I have a free body diagram of a cart being pushed and accelerated to the right with friction present. So here's my cart. Again, it is on the earth, so I have the force of gravity down. It is resting on the ground there, so I have the normal force up. It's being pushed to the right, so I have a applied force to the right, but I also know that friction is present. So I'm going to draw that friction vector in first. Now I know that it has an applied force to the right because it's being pushed to the right, and it says that it's being accelerated to the right. So what this tells me is that my unbalanced force, the direction of the net force, has to be to the right because that's the direction of acceleration. Acceleration direction has to equal the net force direction as well. So that means that my applied force has to be larger than the friction force. And that way, my unbalanced force, my net force, is in the same direction as that acceleration, which the problem tells me is to the right. So that's my finished free body diagram for a cart being pushed and accelerated to the right with friction present. Example number 7, draw a free body diagram of a cat falling from a tree, and we're ignoring air resistance. Don't worry, cats land on their feet, so he'll be fine. Now here's my cat. I know, it's a beautiful cat. Sometimes I like to draw ears on the free body diagram on the box if I'm feeling fancy. And then I know that this cat is under the influence of gravity, right? This is why the cat falls to the ground from the tree, is because the force of gravity is pulling downward on that cat. Now, if we were not ignoring air resistance is similar to friction in that it opposes the motion of the object, meaning that it would be pointed upward. But here we're ignoring air resistance. So are there any other forces acting on this cat? Nope. That's it. That's our free body diagram. Cat falling from the tree. Example number 8, draw a free body diagram of a skydiver before she opens her parachute. Air resistance is present, but she has not reached terminal velocity, which means she is still accelerating downward. So I have my skydiver. She has jumped out of the plane and she is falling towards the surface of the earth because of the force of gravity, okay? So that, again, she's under the influence of the force of gravity. That is the force that's pulling her down towards the surface of the earth, causing her to accelerate downward. Now, it says air resistance is present, but she has not reached terminal velocity. Now, terminal velocity is when we have reached a velocity in which we're not accelerating anymore. So it's just a constant velocity if you're skydiving. So here it says that she's still accelerating downward. So we know that our net force has to be in the direction of acceleration. So therefore, the net force, the more force, right, the longer force vector has to be pointed downward. So that's the direction of our acceleration. So therefore, our force of air resistance is upward because we know just like friction, it opposes the motion, and it's going to be a smaller force and therefore my net force is down and my acceleration is pointed downward as well. And then finally, last but not least, example number 9, we want to draw a free body diagram of a skydiver who has reached terminal velocity. Now, like I said before, terminal velocity is when you reach a velocity that you can't go any faster. So meaning you have a constant velocity. You reach that velocity where it's constant now. There's no more acceleration. Now, terminal velocity has to do with the speed of the object. So the faster a skydiver falls, the more air resistance is involved. And then it also has to do with the amount of area, which is why skydivers, when they open up their arms like this, they slow down usually when they're at terminal velocity. And then when they go like this, they speed up, because the more area they have, the more air resistance, and therefore the less the terminal velocity. So if we've reached terminal velocity, we know that we have to be going at a constant velocity, which means that there's no acceleration, which means that forces are balanced. So here's my skydiver. Again, the force of gravity is what is pulling that skydiver down towards the earth. And then, like I said, because we're at terminal velocity, we're at a constant velocity, there's no more acceleration, therefore forces have to be balanced. And therefore, the force of air resistance has to be the same size as the force of gravity.